Welcome to my talk, How Simple Should Using Ferrite.jl Get for FerriteCon 2023 in Bochum. My name is Knut Andreas Meyer and I'm a postdoc at the Institute of Applied Mechanics at TU Braunschweig. Last year at FerriteCon here in Braunschweig, we discussed how can we reduce the amount of boilerplate code needed in order to write a Ferrite program. In this talk, I'll show you what I've been working on in order to achieve this goal over the last year. So what you see on the first page here is a complete finite element program written in Julia with Ferrite, in addition to some packages that I will describe today. So, how does writing this with these packages compare to doing it with, say, pure Ferrite, hard-coded for the specific example? It's not that many lines of code, but we do see that there is a quite significant reduction. The main purpose, however, of this reduction is that we can now easily change, using some small changes to the input, what is going on in the background. And this flexibility is really what we're after. So first, before I show the contents of this talk, just see that this little code snippet actually produces a solution, which is nice. So, what actually happened here? We start with the Ferrite.jl syntax. So if you're used to this, to Ferrite, you'll be quite familiar with this one. Then we use the FerriteAssembly package that I will discuss later, where we define a material. Normally you need to do a bit more, but here's an example material, and we define a domain that we're going to work on. Then we use FerriteProblems to create a problem, and FESolvers to solve that problem. And then we use a package I won't discuss, which is not mine, FerriteVis, to actually visualize the results. So I will start this talk by introducing this so-called ecosystem built on top of Ferrite. So that's FerriteAssembly, FESolvers, and FerriteProblems, where I will focus mostly on FerriteAssembly. And then I'll show a few examples from research, one from fun, and that it maybe to prove that it works. And then I'll give a bit of a conclusion outlook in terms of what are the challenges in the design, and when would I recommend using these or some of these packages. So with that, let's get started on FerriteAssembly. So the main purpose of FerriteAssembly is that you have a function called work, you have a worker, which tells you what to do. So do you want to assemble your global equation systems, or do you want to integrate just some function? And then where to do it. You want to do it over the cells in Ferrite, or do you want to do it face? If you've seen Abdullah's talk on the interface or discontinuous Lagrange approaches, in the future hopefully we'll have an interface domain as well. And then you'll need to give the current and all degrees of freedom if needed, if you need that information. And then the user will normally define, for example, for a cell domain, either the element routine or the element residual. And these are then functions that you dispatch on your specific material type. In the initial example, this was the example element of the weak form. You could alternatively, or in addition, implement phase routines, where you want to evaluate contributions from the phases into your global system. Or if you want to integrate things, you can integrate a cell or integrate a phase in a similar manner, except that then in addition to the material, you might for one material want to do different things. So we can also dispatch on this val, which will be your type in most cases. So to use it, then we need to know what I said. Worker, I think, is quite clear. Either you integrate or you assemble. But what is a domain? So if you see in the talk on mixed grids or the subdof handler, you know what that is now. So we do require that one domain has only one subdof handler. we also need the same FE values, so same cell values, for example. So it means in addition we require the same quadrature rule. And we need to have the same type of material. That means the same, typically the same weak form. In Julia terms, it has to be the same type. That's the main point. So if we now have a grid, say we have two physical domains, we have an inclusion in the center, we have a matrix around, and we have two different types of elements, some triangles, some quadrilaterals. Then we now have four different domains. So in the first we'll have, of course, the subdof handler, which needs to be one for all the triangles, quartets, and we have the inclusion material, since it's the red ones here in the center. We also have the same material for the quadrilaterals in the center, but we have a different subdof handler, so this has to be another domain. And the same then for the matrix material. We have to split that into two, but note that we can have the same subdof handler used in two different domains. That's no problem. So how to define these domains? Well, you set up the domain spec, which basically consists of give it your dof handler if you only have one subdof handler in your domain. If you have multiple subdof handlers, you need to use the subdof handler. You give the material, you give it your FE values, so say cell values or face values or whatnot. Potentially you might give it a set, some other information. So if you want to be just a part of the domain, right, then you need to tell it where is this. Another thing is then you'll set up, using this domain spec, you'll set up your buffer that contains all the values. And this buffer basically contains a lot of information. One of them that I just quickly highlight is contains this so-called item buffer, which depends on the domain you have, will be, for example, a face buffer or a cell buffer, containing a lot of additional information that allows you to customize your subroutines, the element routine, face routine, etc. So, if we now change, how do you do this now for multiple domains? Now we only have one domain. Well, for example, you just set up one domain spec for each domain, and then you give that to the setup domain buffers function, giving a dictionary containing your domain specs, and the rest is the same. And what changes you get now, instead of a domain buffer, you get a dictionary of domain buffers, but all other functions will work as usual on this. So how do we make this multi-threaded? Well, we just say threading true, and then things change into a threaded domain buffer, but again can be used the same way from top level and from the bottom level. So let's do some actual work then. Now we talked about this work function, so let's do it. So we use the regular Ferrite setup here, nothing special. And now we're going to also use one of the example elements, a stationary Fourier case, which contains the heat conductivity. So we set up our domain buffer the regular way. We want to create an assembler, so we use the standard Ferrite syntax to start assemble, and then we do the work. And then we're gonna apply the boundary conditions and solve the problem. And this is the solution. And for those of you that are super into the Ferrite documentation and seen the heat flow example, you notice that I never specified the actual body load here. And the stationary Fourier element only contains the conductivity, doesn't have any production terms. So instead of having to do that in every element, FerriteAssembly also allows you to instead use a load handler, which works very similar to the Ferrite's constraint handler, except that it adds your external loads to your problem. So in this case, we'll add a body load to our load handler, and we apply it to add it to the residual, and then we solve it, and we get back the solution of the example in Ferrite. But now I only talked about assembling. I also said you can use for integration, which is quite nice. Let's say we now want to calculate the average temperature here. So obviously that's defined as an integral measure, but we have our cell values with the quadrature and everything, so we can integrate. Here we'll use a convenience integrator called the simple integrator, where we just define it, where we note that the first part of that function returns 1, which is just will give you the volume, and the other one returns the actual degree of freedom, so U, which will give then the integrated temperature, and the quota is the average. So that works pretty nicely like this. And just finally, it's quite nice sometimes if you have a complicated material, you don't want to calculate all the derivatives, you want to use automatic differentiation. So you can assemble, for example, on the cell domain, you'll define just the element residual. And if you do that using standard automatic differentiation, using forward diff here, you'll end up with a time something like this, which compared to the analytical tangent allocates a lot and takes more than twice as much time. But FerriteAssembly comes with a nice special buffer that allows you to pre-cache some of the values, which just will bring the time down to almost as fast as the analytical tangent in this case. And the only difference is you need to specify when you set up your domain buffer to use auto-diff buffer true. So, to sum up FerriteAssembly, you see there are some examples, there's some documentation online, so feel free to check that out. Just to connect to Fredrik's talks on what has changed in Ferrite recently, I also like to just mention that if you, for example, want to use this local constraint application, you can actually use a custom assembler that allows you to give the constraint handler, which will then automatically apply all the constraints locally instead of having to call apply after assembly. So, to give a quick summary of FerriteAssembly, we do the first thing you need to do is you need to define your material type. Of course, normally you wouldn't just use something that is in the example materials, that's just for trying it out. You'll need to define your low-level routine. It could be an element routine, phase residual, integral cell, whatever. Then you use your standard Ferrite setup, so DOF handler, constraint handler, FE values, etc. You're going to set up your domain spec and domain buffer, and then you create your worker, and then you call work on the worker and on the buffer. And that's it. That's what it does. And you can use this for a lot of different stuff. So, a bit quicker now for the two other packages, because we're running already a bit short on time. So, FESolvers is a package that basically says, you give me a problem that follows a certain, that you define your problem structure, and all it needs to do is it needs to overload a set of functions to at any time do whatever FESolvers asks it to. So for example, update the problem or return the current Jacobian, or for example, do post-processing if you want to save something. And then you have to define a solver. So you do that, and then you just solve the problem. So I won't go in too much into details here. I'll skip directly to the next, which is FerriteProblems, which is basically one of those problems. Let's say here my problem. This already defines that problem and all the functions, where you instead give it the input that typically comes from FerriteAssembly plus some other Ferrite stuff. So you have the standard Ferrite setup, then you do the FerriteAssembly domain spec, and then you give that to FerriteProblems so that it can create your problem. And then you solve it using FESolvers. So, this part here is in. So, if we now would like to do this, and let's extend what we did earlier. So, we take what we have, but now we define a post-processing struct that we want to output things to ParaView here. And then we're going to overload this post-processing function so that each time step that's solved will basically write to VTK. And we'll need to close it, and then we define now our problem, with the only difference is we added now this little post-processing part. We do then the same, we do solver, and we solve the problem, and we can actually now get the time evolution of this initial problem that we had in the beginning. So with that, let's get over to a few examples, so to say, for research and for fun. So first, one thing that we're working with at our institute is concrete, and specifically frost damaging concrete, where we are interested in what happens when we have a moist concrete and it's filled with water, and this water freezes, and as you know, that will expand, and that can cause fracture. So we're not going to resolve the pores now. We're going to model this as a homogeneous porous media. And what we do is then we have the mechanical equilibrium from linear elasticity, we have mass conservation, and we have the energy balance. And specifically, we add upon this the phase transformation of freezing thawing, getting volume expansion. So if we do that, you see our very preliminary initial results where we have insulated this bar. This is a 1D example technically, so it's a wall. And on the left side, we're cooling. So the top graph shows the temperature, where you see the initial temperature in orange here is plus about 10 degrees. But then we freeze it from the left, and you can see how the little white line in the center is actually the point where water starts to freeze. Then what's interesting is if you look in the two lower portions, then you can actually see the pressure of the water, and in the lowest the actual stress on the concrete. And you can see that we develop, due to the freezing, we get this kind of stress wave propagating through the material, which is due to the water expanding, but due to the ice on the left hand side, it cannot escape the wall. So it's getting pushed, it's expanding, and the water has nowhere to escape. Okay, so next example, we work on highly nonlinear problems as well. So the partially saturated porous media case, where here you see some suction problem, where we suck our water up into our a column of a concrete, and you can see how the time evolution are. This is CT scans. And the problem here is that if you look at the pressure, the capillary pressure as a function of the saturation, it changes in the range of 6 to 7 orders of magnitude here. At the same time, the remaining or the relative change in permeability changes by 20 orders of magnitude almost. So this is an extremely nonlinear problem, and it's very hard to solve. So what we can do, we now define a Newton solver. So that's the standard choice, Aristotle Newton solver. And the residual evolution looks like this. So it basically doesn't converge. Nothing happens. An alternative is using so-called Picard or fixed point iterations. This is slower, but it is much less sensitive to the initial guess. So you can see it actually goes fairly steadily down here, the residual. But then what we do, which is quite nice, is now we could actually couple these two. So you make a multi-stage solver, where we do first the Picard iterations down to 1e minus 4, and then we go to 10 to the power minus 10 using the Newton solver once we're getting close to the solution, and you see how it jumps down. And finally, mostly for fun, take brittle fracture. We take the model from Barali et al. And we combine that with Elias' IGA package, which is actually compatible with Ferrite assembly and then also Ferrite problems. And we can actually simulate now fracture plate with a hole. So we use symmetry conditions here, and you can see how we can nicely simulate now this fracture using phase field and IGA, which I thought was quite cool. So, getting to the end of my talk, what are the challenges? Well, what if there is a bug in the user's element routine? So this function looks fairly harmless, but these are the problematic parts here if we want to use automatic differentiation. So this is the residual. So let's say we want to do automatic differentiation to get a nice result out of this without having to implement the derivatives. So then U will be a dual number from forward diff. And thus E, this energy, will become a dual number. And then we try to assign a dual number to a vector of floats, which does not work. And what happens is that you get an error message. This is 1/6 of it. This is the full one. And as a new user, you go like, okay, shit, this code doesn't work. What's going on? And yes, we try here to tell you some at the beginning that maybe this is because you did this mistake, because it's a quite common mistake. But this is still a problem, I think, for a new user. And now, of course, what if your problem is not converging? Well, at first, it's quite nice to have this package. For example, using FerriteAssembly, you can use a relative tolerance for each field based on the LP norm of the synodal force contribution, which really helps out when you have multi-field problems. Using FESolvers, you can, for example, use an adaptive time stepper. This based on Elias' algorithm. You can use line search as contributed by Maximilian Köhler. You can use improved initial guess strategies, a bit under development still, but they still work quite well. You can even start implementing quasi-Newton iterations, even adaptive switching, as I showed before, which is also under development. Or you can implement your own custom solver. But before you go down here, you're probably going to start stepping through all the packages. And that's when it gets a bit tricky to use. So if you have to step through the packages that you're using to understand why your things aren't working, I think that's a sign that the package isn't really mature enough, or it's not working out as nicely as it should. You need to be a developer almost to use it. So who should use it, or when should you use it? So let's say you're a bachelor student or an introduction master student. You just want to get into finite elements. You want to solve some simple problems. So probably focuses on physics. Typically might of course be nonlinear problems, but typically easy to converge. Sure, use it. I think these packages will help you, but you could technically also just use a more commercial tool. So it depends a bit. If you just want to get into a bit, it could be nice, but if very soon you'll get into the next level, you actually need to understand. So new PhD student, advanced master students, you really want to understand the finite element, the nonlinear iterations, everything. So then the key is you don't want to use all this high level stuff because you want to understand what's going on. So then I wouldn't recommend using it then because as you want to progress, you want to gain that understanding of what's going on in Ferrite and Julia. But once you start and written multiple Ferrite problems, you're getting used to it. Now you're going to start tackling a larger variety of problems. You're going to build up your bank of different softwares. You want to have something that's a bit more scalable. You want to be able to customize things, but you don't want to write everything from scratch like everyone else has done before. Then I think this is the main user group. Like, you reduce the risk of bugs, you have fewer design iteration, because at least in my opinion, having something that somebody thought through helps out. And what I'm presenting here is one option. And of course, everything is open source, so at any time you feel this isn't working for me anymore, you can opt out by just make a branch, make a fork, and keep working on your own if you don't like it. But the longer you can stay in, it has some advantages for sure. And of course, if you're a Ferrite developer, you need hackable solution. You have deep understanding of Julia. I like my own code best, of course. Why would I use someone else's code? But at the same time, well, you can still reduce the risk of bugs. And at least when it comes to my packages, I'm always happy to have BRs or issues or whatnot. So getting to the final remarks. FerriteAssembly performs work on domains efficiently. That's the main purpose. Reduce the boilerplate code for looping over your domain in different ways. FESolvers is for solving the nonlinear, say, quasi-time-dependent problems. FerriteProblems define that problem specifically for Ferrite and FerriteAssembly. So FerriteAssembly, I think a package like this, so could be this one, could be another one, would really benefit the Ferrite community because it would give a common interface for defining physics. So your element routines can be shared. It's super quick to try someone else's code. and it does remove a lot of your boilerplate code for doing, say, boring tasks like, I want to integrate something over the domain. I want to figure out what's the flux across the boundary. And you don't want to write a custom loop every time you do that. You can just, in that case, use a simple integrator. If you have a bit more advanced workflows, you can build on top of that, having custom workflows with the advanced integrators. But I would say it's still in development, and if you are interested, please take a look. If you find any things that you say, this assumption doesn't work for me, then let me know, and maybe we can find a way to make it more general, but still keeping it easy to use. And FESolvers Ferrite Problems, I have found it very hard to make this general, hackable, and easy to use at the same time, and easy to understand if things go wrong. So I would say currently it's really good if you're using FerriteAssembly, you can just jump into this super quickly by giving the input, and you can check that your implementations are working. But it's still in development, so use with care. And again, it's not really possible, nor the aim, to be competing with commercial codes, right? So we still want to have a white box type of code and not just bunch everything into hidden dependencies. So with that, I would like to thank you for your attention, and I look forward to the questions.
Yeah, are there any questions? So?
Well, there's maybe no secret that Ferrite is a bit inspired by Deal 2, and in Deal 2 they quite recently added these things called mesh workers and loop and so on, which is a little bit similar to this in that you kind of give a callback to what you want to do on every cell, or a callback to what you do on every phase and so on, and then you do like loop with these callbacks, and that does the whole thing for you. So then you don't have to write the loops yourself and so on. And it also means that you kind of abstract away the way that the loop will actually run. Like maybe you want to run it parallel or something, you don't have to code that, it's just an option to this loop. So I'm wondering if it would make sense to look a little bit on that and see if that could be also an idea to structure things to make it easier. Because then your problems here would kind of be like a set of callbacks only, like let's say a heat problem would be a callback with what you want to do in every cell and what you want to do in every phase and so on. And that would maybe be something that would be interesting to.
Yep. No, I think it's funny. I had the same comment from my previous office mate. But I should, first of all, I should actually acknowledge first, Fredrik, and all the nice discussions we had when doing this. And I think this part of more kind of generalizing it to not just being assemblies is definitely that. What I would say to defend the approach I chose with having this dispatch type of a material that you have to dispatch on is really because I find it's a really nice way that you can write if you have a class of materials you're working on, then you can have your library for example, say phase field modeling, right? You can have that library and that contains all the physics you need for that type of problem. And then that kind of naturally just falls in. You don't have to write out that it's a specific function, and it might be that it's nice also with the more functional type, if I understand you correctly, that you're actually passing the function object.
Yeah, I mean, if you use dispatch or functions, I guess it doesn't really matter. It's just a way to run some user-provided code. So,
but yeah, for sure. But I think it does in a way have quite some similarities. Maybe except that I think at least Fredrik, you said that they loop over everything at the same time, both interfaces and cells. And here it's a bit more separate. That you talk about one domain, what you want to do on that domain. So it's different choices, and I think that's. I'm not sure if I see big pros and cons, but happy to discuss more also later.
Any other question?
So if no one else has a question, then I have a theory question about the Newton solver.
Yeah.
especially the switching from the Picard iteration back to the Newton.
Yeah.
We have some theory for this one on when our optimal time points to switch back to the Newton.
No. No, basically, so I mean, I've seen in the literature there are some that have done it, of course, and the simplest option I've seen is do it after X number of iterations.
Okay.
What I did is define a tolerance and number of iterations, so you can of course choose, say, do maximum 100 iterations or stop when you get to this error. What is quite effective is actually to do a few regular Newton iterations first, because often, if you're lucky, it's going to work super fast, so there's no point in spending time in the slow method. But I think this field is really endless in how you can come up with different schemes.
Yeah, sure. I was more thinking about if there is actual theory about this one, because I
think it's really
schemes, so
I think it's really problem dependent, because you do need to know something about, say, the convexity of your problem in the area around your solution. And by the time you know the convexity, if you want to do that numerically, I think that's just going to be more expensive anyway. So you would need to know it. And I think if you know enough that much about your problem, you probably can go to your solution quite quick anyway, I would guess. But
Before we start, then let me comment one thing. Why did you call the Picard iteration, or why you coded the Picard iteration as a specialization of a Newton solver? At least to my understanding, then you can basically encode everything as a Newton solver. But I would, because the tension maybe for gradient solvers is then just constant, and in simplest case identity.
Yeah. So in this specific case, it's actually a modified Picard iteration. So it's like it takes part of the gradient into account, but not the full expression of the gradient. But the reason why I just have it as Newton solver is basically, well, you start with Newton solver, and then the way I've now implement, which is a bit still not fully set the interface, is that you basically do a switching of the material. Is you change the material setting in your material, and then you're actually calling different calculations on the material stiffness depending on that, and then it just kind of naturally follows exactly the same structure as a Newton solver. So it's more laziness and convenient to have the same solver.
Thanks, and let us